Hello, welcome to S Chemistry. I am your instructor Dr. Suhas Gauri, and today I will be teaching BSc 5th semester Physical Chemistry course on nanomaterials. So here is the outline. In this class I am going to cover method of synthesis of nanoparticle. So here I am going to cover two types of methods. One is physical vapor deposition with consolidation, then followed by chemical vapor deposition. So let's start with physical vapor deposition with consolidation. So as the word suggests, physical vapor means your whatever the material that is coming into the vapor form, that's getting deposited with consolidation. Now we will see the how the technique works. So this technique basically involves a use of material of interest as source of evaporation. So for evaporation, we have to use as inert gas or reactive gases for collision with the material vapor. So that is the condition. So you have to use inert gas or reactive gas. You can use. If you are taking a reactive gas, it will form with your nanoparticles. That is the side product will form or main product will form after reaction. So generally, the reactive gas is nothing but your oxygen. So in terms of if you have to make the some particle oxidize element oxidize, then you can use the reactive gas. Otherwise, you can use the inert gas for evaporation. So there will be the cold finger on which cluster or nanoparticle can condense. So after evaporation, you will be having one cold finger, so on which your cluster or nanoparticle can condense. So whatever the nanoparticle that he has to form or synthesize, it will go to on cold finger. So you will get nanoparticle there. As a scraper or to scrape the nanoparticle and piston away and anvil, an arrangement in which nanoparticle powder can be compacted. So usually metals or high vapor pressure metal oxide are evaporated. Generally there are some metal oxides that is used to get evaporated. High vapor pressure with high vapor pressure. Or you can directly sublimate from filaments or boot of refractory metals like tungsten or thallium and molybdenum. So these three types of metals are there where they use as a refractory metal. So in which material to be evaporated are held. So these are the like material of the container: tungsten, thallium or molybdenum. So these three types of materials are generally used to synthesize the nanoparticle or to make the high vapor pressure metal oxide to get evaporated. Next point is the density of the evaporated material close to the source is quite high and particle size is small, that is less than 5 nanometer. So whatever you are making evaporation, that density should be evaporated material close to your the source and it is quite high. So therefore your particle size will be less than 5 nanometer. It will form. Now we will see what is the point we have to take in account to synthesize a uniform nanomaterial. So in general, the rate of evaporation and the pressure of the gas inside the chamber that determine the particle size and their distribution. So distance of the source from the cold finger is also important. So how can you control the nanoparticle size? So using rate of evaporation, that is the first your parameter. Second parameter is the pressure of the gases inside the chamber. So this is the second parameter. And third parameter is the distance between source and the cold finger. So how much distance is there depending on that how much thin layer you want to synthesize. So based on these three parameters we have to decide. So what is the advantage of this technique? The particle size can be controlled by adjusting the pressure of the inert gas or the rate of evaporation and the distance between the source of the evaporation and the central cold rod. So on these 4 points, so these are the variables where particle size is dependent. Second point is amorphous or crystalline nanoparticle. So these both type of nanoparticle can be synthesized by the controlling gas pressure in deposition chamber. So if you control the gas pressure, uh, if it's high, you will get the crystalline. If it's high, you will get amorphous. If it's slow, you will get the crystalline material nanoparticle. So you have to just control the gas pressure inside the deposition chamber. So this is the general schematic diagram of synthesis of nanoparticles by physical vapor deposition. So as you can see, this is your chamber. So this is your, you have to attach this chamber with vacuum pump just to remove whatever the inside reactive gases is there, and then after this complete applying vacuum, we have to put the some gas. That is, for that we have to have this gas inlet. So using this inlet, you can purge your gas inside the chamber. So this is the piston and wheel. So for this, the use of this is just to adjust the distance between your funnel and the cold finger. So this distance you can control using this piston. So this is the funnel where your material will get evaporated or get heated up. So based on this temperature, you can decide your rate of evaporation. So side there will be crucible. So crucible has the work just to crush the material or just to evaporate the nanomaterial in uniform form. So this is the cold finger, where inside cold finger you will be having liquid nitrogen. So this is the central rod, and this is very important in terms of to get your condensation at particular time or fixed temperature. So based on this temperature, your nanoparticle size will be dependent. And this is the scraper. So in this scraper, this is important just to adjust the height of the cold finger. So these are the parameters and component of the physical vapor deposition chamber. Moving to the next topic, now we will see the method of synthesis of nanoparticle using chemical vapor deposition method. So what is my chemical vapor deposition method? So this method is about a chemical which get react in vapor form. So deposition take place in vapor form. So the definition is given here. A hybrid method using chemical in vapor phase is conventionally used to obtain coating of variety of inorganic or organic materials. So this method is hybrid. So it's both physical and chemical. So both methods are mixed. So here your chemical first get in vapor phase, and this is conventionally used to obtain the coating of a variety of inorganic and organic materials. So now we will see what are the basic chemical vapor deposition processes. So as you can see in figure 5.3, it's given here. So this solid dots represents the gaseous reactant, cross dots represent the intermediate product, and blank dot represent the solid product, and square symbol represent the gaseous product after reaction. So now we will see the method with step by step how it's are going to fall on this substrate. So this is the first point. First, your transport of reactant vapor towards the substrate will come. So these are the solid dots. These comes to the towards the substrate. So this is the first process. Then this reactant get cracks into different product on this high temperature surface. So this substrate surface is having a very high temperature. It get cracks on this surface, and after getting cracks you will be having multiple products. These products get diffused on the surface and undergo some chemical reaction with other. So after reaction, chemical reaction, it start getting nucleate, and nucleation will take place, and it will grow to form the desired material films. So as you can see, these solid products formed, and it is forming a particular desired film. So this is because of nucleation, and further, if you this process continues for a long time, this will grow and form the thin film. So this is the gas inlet. So with this reactant, you are coming with a gas, inert gases, and here it get reacted and form the films. So after forming film, you will be having some byproducts created on the substrate that has to have to transport back to the gaseous phase. So this square is your byproduct. So these byproduct are going outside the sample, outside the substrate. So it will go in the vapor phase, and that's or gaseous phase, and that's how your CVD process is going on. Now we will see there are two types of processes are there. So one is hot wall chemical vapor deposition, and second type is the cold wall chemical vapor deposition. So this is the schematic representation of hot wall chemical vapor deposition, and this is the schematic diagram for the cold wall chemical vapor deposition chamber. So in both cases, you will be having vapor inlet and exhaust, it is outlet. So the only difference is your outside the wall will be having some heater, and in cold wall you will not be having this kind of heater. Now we are going to see what exactly happens during the process. So as you can see in this figure, the vapor of a desired material may be often pumped into reaction chamber using some carrier gas. In some cases, reaction may occur through aerosol formation in gas phase. There are various processes such as reduction of gas, chemical reaction between different source gases, or oxidation, or some disproportionate reaction by which chemical vapor deposition can proceed. So these are the four types of reaction can happen in the this hot wall chamber. So however, it is preferably that reaction occur at the substrate rather than in the gas phase. So usually 300 to 1200 degrees Celsius temperature is used at the substrate. So I am talking about this substrate temperature that can be go 300 to the range of the substrate temperature is the 300 to 1200 degrees Celsius. So there are two ways is there. So one is using heater, another is using a filament. So in hot wall setup, the deposition can take place even on a reactor wall. So your deposition can take place on reactor wall also. So this is avoided in cold wall design. So here your substrate will not get your reactant will not get deposited on cold wall. So this is the plus point for the cold wall diagram. So besides this, the reaction can take place in a gas phase with hot wall design, which is suppressed in cold wall setup. Further, coupling of plasma with chemical reaction in cold wall setup is feasible. So coupling of plasma in this here, it is possible in cold wall setup. So usually gas pressure in the so inside some particular gas pressure will be there, so that the range is from 100 to 110 to the power 5 pascal are used. So growth rate and film quality depends upon the gas pressure and the substrate temperature. At intermediate temperature, it is limited by mass transport, that is, supply of reacting gases to the substrate. Here, the reaction is faster and supply of reactant is slower. So, growth rate produce at high temperature, growth rate reduces due to desorption of precursor from the substrate. So these are the two differences are there for hot walled chemical vapor deposition and cold walled chemical vapor deposition. Now we will see advantages of chemical vapor deposition. So this technique is widely used in industry because of the following reasons. So first reason is it is a relatively simple instrumentation. Second is the ease of processing. So the process is very easy. Third point is possibility of depositing different type of material. So here various type of possibilities are there to for the deposition of material. Fourth point is it is economically viability is there. So that's why this is widely used in industry. So for example, if you want to make nanocrystalline films or single crystalline films, you can use this kind of method. So that is the chemical vapor deposition. Now we will see what are the variants of chemical vapor depositions are well known in the literature. So first variant is the metallo-organic chemical vapor deposition, that is MOCVD. The second variant is their atomic layer epitaxy, that we also say that ALE. Third point is vapor phase epitaxy, that is denoted by VPE. The fourth variant of chemical vapor deposition is plasma enhanced CVD, or in other words, PECVD. So they differ in. So these are the four type of models are there or variants are there, where you can either change the source of the gas pressure or the geometrical layout and the temperature, what are the temperature we are using for that. So these are the three different parameters are there. So with these three parameter, these four variants are uh, can be changed, and relatively you can get the your nanocrystalline material or films. Here we come to end of this lecture. These are the references for images and these are the references for content for the given lectures. So I thank you for kind listening. See you in next lecture. Till then, happy learning.